Welcome back, traveler. Tonight we explore a pattern so familiar it barely registers as a question. Every planet, from the scorched inner worlds to the cold giants far beyond, moves around the sun in the same direction, counterclockwise, if you look from above the sun's north pole. It feels tidy, predictable, almost polite, like traffic flowing smoothly around a roundabout that's always worked this way. Most of us absorb this as just another rule of the solar system. Planets orbit stars. They line up, they behave. Textbook diagrams reinforce it, frozen and clean, as if the universe itself prefers neatness. And once you've seen enough of those diagrams, the idea stops feeling remarkable at all. But here's the fracture most people never stop to notice. Nothing in the universe had to turn out this way. There is no universal rule that says planets must orbit in agreement. No cosmic law that forces chaos to organize itself into a single shared direction. In fact, if you imagine worlds forming independently, collisions piling on collisions, the expectation should be mess, not alignment. If this shared direction is not required, then it must be telling us something. Something about how the sun was born. Something about how motion behaves when gravity takes control. Something about why disks form instead of clouds. Why rotation survives collapse. And why the solar system remembers a spin that began before any planet existed at all. By the end of this journey, you'll understand exactly why every planet goes the same way. Why the exceptions elsewhere in the universe matter so much. And how this quiet agreement in motion is really a fossil, a preserved clue from a time when the sun didn't yet exist, and nothing had settled into place. If you're enjoying this kind of late-night thinking, like the video, subscribe, and leave a comment telling me where you're watching from and what time it is for you. Now, let's begin. For most of human history, this shared direction didn't look like a mystery at all. It looked like order. When ancient skywatchers tracked the planets night after night, they noticed patterns long before they understood causes. The wandering lights followed the same general path across the sky, looping and drifting, but always confined to a narrow band. It felt natural to assume they belonged to the same system, moving in harmony, because that was simply how the heavens worked. That intuition carried forward even as models changed. When the sun replaced Earth at the center, the sense of harmony stayed intact. The planets were no longer carried on crystalline spheres, but they were still imagined as obedient participants in a well-behaved cosmic dance. Same plane, same direction, same rhythm. It felt like evidence of design, or at least of inevitability. And yet, if you slow down and strip away that familiarity, the situation becomes deeply strange. Imagine not a finished solar system, but the raw ingredients before it existed. A region of space filled with gas and dust, cold and diffuse, drifting among countless other such regions. No planets, no sun, no reason for anything to agree with anything else. Just particles moving in every direction, nudged by tiny gravitational tugs and random motions. In that picture, alignment should be rare. Collisions should cancel motions out. Directions should average away. If anything forms at all, it should wobble, tilt, or tear itself apart. So the real question sharpens. How did all that randomness collapse into something that spins cleanly in one direction, and then somehow convince every planet to follow along? At first glance, gravity seems like the obvious answer. Gravity pulls things together. It builds stars. It gathers material. But gravity alone doesn't choose a direction. It doesn't prefer clockwise or counterclockwise. It doesn't explain why collapse leads to rotation instead of stillness. In fact, gravity by itself would happily pull everything straight inward, erasing motion rather than preserving it. This is where our everyday intuition starts to fail us. We tend to imagine collapse as a straight fall, like rain dropping vertically into a bucket. But space doesn't behave like that. Nothing falls straight in unless it starts perfectly still. And in the real universe, nothing ever does. Every particle carries some sideways motion, no matter how small. A gentle drift, a slight offset, a microscopic imbalance. Those tiny sideways motions matter more than you might expect. Picture ice skaters drifting slowly toward the center of a rink. If they pull their arms in, they don't stop spinning. They spin faster. Not because something pushed them, but because their motion had nowhere else to go. What was spread out becomes concentrated. What was subtle becomes dominant. The same thing happens on cosmic scales. As a cloud of gas begins to collapse under gravity, its overall rotation, however faint, cannot simply vanish. There's nowhere for it to go. As the cloud shrinks, that rotation speeds up. The entire structure begins to flatten, not into a sphere, but into a disk. Material moving in the same general direction settles into a shared plane, because that's the only configuration that remains stable. This is the first major crack in the old intuition. The planets don't orbit the sun in the same direction, because the sun told them to. They orbit that way because the sun and the planets were born together from the same spinning disk. The direction came first, the star came later. But that raises another problem. If all it takes is a little initial rotation, why don't we see chaos preserved as well? Why didn't chunks of material keep wildly tilted orbits, slicing through the disk at odd angles? Why did the disk become so clean, so orderly, so dominant that nearly everything fell into line? The answer lies in friction, not the kind you feel when you rub your hands together, but its quiet cosmic cousin. Inside that collapsing disk, particles constantly collide, exchange energy, and damp out extremes. Orbits that stray too far get nudged back. Motions that cut across the flow get absorbed. Over time, the disk doesn't just spin, it self-corrects. It punishes rebellion and rewards cooperation. You can see a faint echo of this process every time you stir milk into coffee. At first, streaks swirl unpredictably, but given a moment, everything settles into a smooth, unified motion. The cup doesn't enforce that order. The fluid does, through countless tiny interactions that erase disorder faster than you can notice. So the solar system's shared direction isn't an imposed rule. It's a survivor, a memory, a fossilized spin from a time when nothing was solid, when the sun was just a dense knot forming inside a glowing disk, and the planets were only future possibilities embedded in gas. And here's where it gets stranger. That initial direction could have been the opposite. Clockwise instead of counterclockwise. Nothing fundamental would change. Physics doesn't can. The fact that we see this direction rather than its mirror image tells us not about necessity, but about contingency, about the specific history of our corner of the galaxy. If that's true, then the solar system is not the template. It's just one outcome. And that means somewhere else, things should look different. Tilted disks, backward orbits, worlds that refuse to cooperate. The question becomes not whether our system is orderly, but how fragile that order really is, and what it takes to break it. And that's exactly where the story takes an unexpected turn. When astronomers began to look beyond our solar system, that expectation was quietly waiting. If disks and shared motion are the natural outcome of collapse, then most planetary systems should look broadly similar, not identical, but recognizable. And for a while, that's exactly what early discoveries seemed to suggest. Planets circling their stars in neat, flattened arrangements, order repeating itself. Then the exceptions started to appear. Some planets were found orbiting at extreme tilts, almost perpendicular to their star's rotation. Others moved on paths that were elongated, unstable, or strangely misaligned. And a few, the most unsettling of all, orbited in the wrong direction entirely. Retrograde worlds, circling their stars against the original spin of the system, like gears suddenly grinding backward. At first, these discoveries felt like mistakes, measurement errors, optical tricks. Surely nature wouldn't build something so self-contradictory, but the data held. And the deeper astronomers looked, the clearer it became that these systems were not violations of the rule, but scars left by violence, because the shared direction of a planetary system is easy to establish, but surprisingly easy to disturb. Picture that original disk again. Smooth, flattened, calm. Now imagine a massive intruder passing nearby. Another star drifting too close. A giant planet forming early and migrating inward. A collision that doesn't just add mass, but injects chaos. In those moments, the disk can warp, planets can be kicked out of plane, orbits can flip. What once remembered a single direction can be forced to forget. This reframes the solar system's calm alignment in a new way. It's not just a consequence of formation, it's evidence of a relatively quiet past. No near miss with a massive neighbor. No late-stage gravitational bullying by an oversized planet. The solar system didn't just form coherently, it stayed that way. And that stability matters more than it sounds, because shared direction is not just about geometry, it's about energy management. When everything orbits the same way, interactions are gentle, close passes are predictable, collisions are rare. Over billions of years, that calm allows smaller worlds to survive. It allows climates to persist. It allows time, which leads to a deeper realization. The fact that Earth orbits in the same direction as every other planet is not a cosmic coincidence layered on top of others. It's part of the same chain of events that allowed Earth to remain intact long enough for oceans, chemistry, and eventually life to emerge. But even this explanation hides a subtler trap. We've talked about direction as if it were inherited cleanly, passed from cloud to disk to planet without ambiguity. In reality, the original spin of that cloud was unimaginably small, almost nothing. A statistical fluke spread across trillions of particles. The universe didn't wind the solar system like a clock. It nudged it. That nudge, amplified by collapse, became everything. This is one of those moments where everyday experience misleads us most. We tend to think large outcomes require large causes. Big systems demand strong pushes, but gravity has a talent for making whispers thunderous. A slight imbalance, once trapped in collapse, can dominate the future of an entire system. And if that's true here, it's true everywhere. Galaxies spin because of tiny asymmetries frozen in during formation. Stars rotate because clouds never collapse perfectly. Planets orbit because nothing ever starts exactly still. The universe doesn't prefer motion. It simply refuses to erase it. Which brings us back to the original intuition, now inverted. The strange thing is not that all the planets orbit the sun in the same direction. The strange thing would be if they didn't, because reversing that direction would require something dramatic. A catastrophe, a rewriting of history. Order, once established, is stubborn. Chaos has to work hard to reclaim it. But that raises a final, unsettling question. If direction is so persistent, so deeply rooted in the earliest moments of formation, then what else around us is quietly remembering a past we never witnessed? What are the motions? Alignments and patterns are not active choices of the present, but echoes of ancient accidents, still unfolding today. That question takes us beyond planets, beyond stars, and into something much larger. To follow that thread, it helps to step back from planets entirely and look at the sun itself. Because the sun is not just the thing being orbited, it is part of the same motion. It spins in almost the same plane and direction as the planets that circle it, as if the whole system were carved from a single rotating gesture. That alignment is not perfect, but it's close enough to matter, close enough to tell a story. If the sun had formed first, fully grown and stationary, and the planets arrived later, this wouldn't make sense. There would be no reason for their motions to match so closely. But that's not what happened. The sun condensed out of the densest region of the disk while everything else was still moving. Its rotation is not a command. It's a memory of the same collapse. This is where the idea becomes quietly profound. Motion came before structure. Spin existed before planets. Direction existed before objects that could follow it. The solar system didn't decide how to move after it formed. It formed already moving. You can feel a faint echo of this in everyday life. Think about pouring batter into a pan while the pan is already rotating. The shapes that form aren't random. They inherit the motion that was already there. Later patterns don't overwrite earlier ones. They adapt to them. In space, gravity plays the role of the pan, locking early motion into everything that follows. And once you see this, you start to notice how deep the inheritance goes. The plane in which the planets orbit, the so-called flatness of the solar system, is not just a geometric coincidence. It's the fossil imprint of angular momentum conserved across billions of years. A physical rule so strict that even the birth of a star cannot violate it. This rule doesn't announce itself loudly. There's no force labeled "keep spinning." There's just an accounting system that never forgets. Once motion exists, it must be carried forward, transformed but never erased. Spread out becomes concentrated. Slow becomes fast. Cloud becomes disk. Disk becomes planet. But here's where another intuition breaks. If angular momentum is so rigidly conserved, why isn't everything spinning wildly fast? Why didn't the collapsing cloud tear itself apart as it sped up? Why did it settle into a stable system instead of flying outward? The answer lies in distribution. The collapsing cloud didn't keep all its rotation in one place. It shared it. Some of that motion ended up in the sun's spin, some in the planet's orbits. Some was carried away by material flung outward or lost through jets and winds. The system didn't destroy its motion. It hid it in different forms. This balancing act is delicate. Too much rotation, and collapse stalls. too little, and everything falls inward. The solar system exists in the narrow middle, where gravity and motion reached a truce, not a perfect balance, but a survivable one. And that middle ground is rare enough to matter. When astronomers simulate star formation, they see countless failures, clouds that fragment too violently, disks that destabilize, systems that never settle into long-lived configurations. The solar system is not the default outcome. It's a successful one, which reframes the shared orbital direction yet again. It's not just evidence of formation, it's evidence of survival. A sign that nothing catastrophic happened at the wrong time. A sign that the early chaos cooled rather than escalated. This calm persistence has another consequence that often goes unnoticed. Because the planets share a direction, their interactions over time remain gentle enough to be predictable. Gravitational nudges accumulate slowly. Resonances form instead of collisions. The system evolves, but it doesn't unravel. That predictability is why eclipses can be calculated centuries in advance, why spacecraft can slingshot between worlds with confidence, why clocks on Earth can stay synchronized with satellites overhead. Order at the largest scales leaks downward into practical reality. And now the simple picture has fully inverted. The neatness we took for granted at the beginning is no longer a cosmetic feature. It's structural. It's historical. It's a constraint imposed by deep physical rules acting over unimaginable time. But one last piece remains unresolved. We've explained why the planets share a direction. We've seen how fragile that alignment can be and how meaningful its survival is. But we haven't yet asked the most uncomfortable version of the question. Why did the original cloud have any net rotation at all? That question doesn't belong to the solar system anymore. It belongs to the universe. To answer that, we have to abandon the comforting idea that the universe ever started at rest, because it didn't. Not locally, not globally, not even approximately. The gas cloud that became the solar system was already embedded in a galaxy that was rotating, drifting, shearing, and constantly reshaping itself. There was no neutral frame, no cosmic pause button. That cloud inherited motion from its environment, the way a leaf inherits motion from a river. Not because the leaf chooses to move, but because stillness isn't an option. Nearby stars tugged on it. Passing shock waves compressed it unevenly. Tiny density variations pulled harder in one direction than another. None of this was dramatic on its own. But together, it ensured that the cloud never collapsed symmetrically. Perfect symmetry is an illusion we invent because it's easy to draw. Nature almost never achieves it. If a cloud were perfectly balanced, with every particle mirrored by another moving in the opposite direction, collapse might erase rotation entirely. But such a cloud would require infinite precision. The universe doesn't do infinite precision. It does leftovers. So the cloud spun, barely, almost imperceptibly, and that was enough. As collapse began, that faint rotation stopped being optional. Gravity squeezed it inward, shrinking the radius, forcing the spin to accelerate. What was once a whisper became a defining feature. The direction didn't emerge during collapse, it was revealed by it. This is where the idea becomes unsettlingly general. The same reasoning applies not just to solar systems, but to galaxies. Galaxies spin because the matter that formed them was never perfectly still. Clusters of galaxies show preferred motions for the same reason. On every scale where gravity has time to act, motion is amplified, not erased. which leads to a quiet but radical conclusion. The universe is not structured on top of emptiness, it's structured on top of motion. Every orbit, every spin, every disk is a response to the same refusal of nature to cancel everything out. Once you see this, the solar system's shared direction stops being a curiosity and starts being a message. It's telling us that history matters, that early accidents are not washed away. They are preserved, magnified, and passed forward. The present is never just the present. It's the accumulated consequence of tiny asymmetries that survived. And there's something deeply human about that. We tend to imagine that large patterns must have deliberate causes, that order implies intention. But here, order emerges from imbalance. Consistency emerges from imperfection. The planets orbit the sun in the same direction, not because the universe prefers harmony, but because it never managed to achieve perfect chaos. That realization also places a boundary on what we can change. You cannot easily reverse a planetary system's direction. You cannot rewind a collapse. Once angular momentum is locked in, it defines what futures are accessible. Some paths are simply closed. This is why backward orbiting planets feel so unsettling. They advertise disruption. They announce that something broke the memory, that a later event overpowered the inheritance. Those systems carry evidence of violence, of encounters so strong they rewrote history. Our system doesn't show those scars. Its planets remember the same spin because nothing ever forced them to forget. So when you look at the night sky and imagine the planets moving, you're not watching a rule in action. You're watching a story continue, a story that began before the sun ignited, before Earth existed, before any solid surface formed. A story written in direction. And now we can finally return to the simple thing we started with. All the planets orbit the sun in the same direction. What once felt like a diagrammatic convenience now reads like a boundary condition of reality, a constraint imposed by conservation, history, and chance working together. It tells us that the universe does not reset between events. It carries momentum forward. It remembers. And in that memory, quietly spinning above us every night, is a reminder that even the most stable patterns we rely on are not guarantees. They are survivors. The door closes softly there, not with an answer that ends the mystery, but with one that shows how deep the roots really go. That lingering feeling says that this explanation sounds finished but somehow not complete, is exactly the right instinct. Because there's one more layer hiding underneath everything we've said so far, and it's easy to miss precisely because it doesn't look dramatic. We've been talking about direction as if it were a property of objects. Planets have directions. Disks have directions. Clouds inherit directions. But direction itself is not a thing you can point to. It's relational. It only exists because space allows motion to be compared, remembered, and preserved. In a universe where motion could simply vanish, none of this would hold. Collapse would erase memory. Every system would begin fresh, disconnected from whatever came before. The fact that planetary systems retain a shared direction tells us something profound about the structure of reality itself. The universe keeps accounts. It does not forgive imbalance. It does not allow shortcuts back to neutrality. This is why conservation laws feel almost philosophical when you sit with them long enough. They are not forces pushing things around. They are refusals. Refusals to let certain quantities disappear. Energy must go somewhere. Momentum must go somewhere. Direction must go somewhere. Even if it becomes subtle, even if it hides, even if it spreads out, it must persist. And that persistence quietly shapes what kinds of worlds can exist. Imagine a universe where angular momentum was slightly less strict, where collapsing clouds could bleed away direction more easily. Disks would be rarer, planetary systems would be more chaotic, long-lived orbits would be fragile, stability would be expensive. In such a universe, the calm clockwork we depend on might never arise. Our universe chose the other path, not deliberately, but decisively. It allows early accidents to harden into structure. It allows gentle imbalances to sculpt entire architectures. The solar system is not balanced on top of physics. It is an expression of physics refusing to smooth everything out. This reframes chance in a subtle way. The direction of planetary orbits feels arbitrary, and in one sense it is. Clockwise or counterclockwise didn't matter, but the fact that a direction existed at all mattered enormously. Randomness didn't disappear. It got amplified and locked in, and once locked in, it constrained everything that followed. The plane of the planets determined collision rates. Collision rates determined growth. Growth determined which worlds became rocky and which became gaseous. Orbital stability determined climate longevity. Climate longevity determined chemistry's patience. Chemistry's patience determined whether complexity could slowly emerge. None of this required intention. None of it required foresight. It only required that the universe remember what it had already started doing. That's why the solar system feels so coherent when you really examine it. Not because it was designed, but because it was allowed to finish a sentence it began billions of years ago without being interrupted. So when we finally circle back to the question, why all the planets orbit the sun in the same direction, the answer is no longer a single mechanism. It's a chain of refusals. Gravity refusing to collapse without consequence. Motion refusing to cancel perfectly. History refusing to reset. The planets don't orbit together because they agree. They orbit together because disagreement was damped away early, and memory won. And that makes the solar system feel less like a machine and more like a habit. One that formed once, persisted, and never found a reason to stop. Now, when you picture those slowest patient orbits tracing their paths through space, you're not just seeing motion. You're seeing the universe honoring a commitment it made long before there was anyone around to notice it. There's a temptation, at this point, to treat that commitment as something static, as if the solar system reached a final configuration and then froze. But even now, the motion isn't finished. The planets still trade tiny amounts of angular momentum with one another. Orbits drift, resonances shift. The system breathes, slowly, almost imperceptibly, across spans of time far longer than a human lifetime. What remains unchanged is the direction itself. That original sense of this way, not the other, has survived asteroid bombardment, planetary migrations, and the sun's own gradual evolution. Even chaos, when it arrived politely enough not to flip the table. This is another place where our instincts betray us. We often imagine stability as rigidity, as something stiff and unchanging. But real stability looks more like flexibility within a boundary. The solar system can bend, but it does not forget. It can redistribute energy, but it does not erase its past. And that tells us something subtle about predictability. We can forecast eclipses centuries ahead, not because the universe is simple, but because it is consistent, because the same conservation rules that shaped the solar system's birth still govern its present. The same bookkeeping that preserved direction then preserves timing now. If you zoom out far enough, this becomes almost unsettling. The laws that decide how planets move are indifferent to meaning, to comfort, to narrative. And yet, by refusing to forget, they create structures that feel almost intentional, not purposeful, but legible. Systems we can learn, patterns we can trust. That trust is fragile. Over even longer timescales, the sun will swell, orbits will shift. The current arrangement will not last forever. But when it changes, it will change honestly, carrying its momentum forward, never cheating the account. So when you return one last time to that opening observation, that all the planets orbit the sun in the same direction, it no longer reads like a diagram label. It reads like a constraint written into reality itself. A boundary condition that shaped everything that followed and quietly limited what was possible. The universe did not promise order. It only promised consistency. And from that consistency, order emerged, not guaranteed, not universal, but durable enough to matter. That shared direction is not telling us how the universe wants things to be. It's telling us what the universe refuses to undo. And once you notice that, the motion above your head at night feels different, less like clockwork, more like memory, still turning, still honored, still quietly carrying the past into the present. Then, without ceremony, the story continues its orbit. And that continuation is important, because it prevents us from misreading the lesson. The solar system's shared direction is not a frozen relic. It's an active constraint, still shaping what can and cannot happen next. Even today, when a comet falls inward from the distant outskirts, its fate is guided by that inherited motion. It doesn't enter a neutral arena. It enters a system that already has a preference, already has a flow. You can think of it like stepping onto a moving walkway at an airport. Once you're on it, every step you take is biased. Walking forward feels easy. Walking backward feels costly. The walkway doesn't forbid either direction, but it makes one path far more natural than the other. The solar system works the same way. Motion aligned with the original spin is rewarded with stability. Motion against it is punished with chaos. This is why most debris eventually settles into the same direction rather than fighting it. It's not forced. It's filtered. Over time, the system selects for motions that cooperate and erases those that don't, not by intention, but by consequence. And that selection effect is quiet enough that we rarely notice it. We look up and see planets gliding peacefully, unaware that this peace is the outcome of relentless sorting. Billions of failed configurations were possible, only a narrow band endured. This idea scales outward in an almost uncomfortable way. The Milky Way itself spins, its stars orbiting a shared center in a preferred direction. That motion traces back to asymmetries present when the galaxy was still forming, when matter first began to fall together after the universe cooled enough for structure to exist at all. Once again, a faint imbalance became destiny. At no point did the universe stop and choose. It just kept going. That's the through line connecting everything we've talked about. Direction is not imposed late. It is inherited early and defended relentlessly. The planets orbit together not because they must, but because nothing ever arrived with enough authority to tell them otherwise. So the next time you see a diagram of the solar system, with its tidy circles and shared arrows, it's worth pausing. That picture is not a rule book. It's a snapshot of survival. A record of motion that managed to persist uninterrupted across billions of years. In that sense, the solar system is less like a machine and more like a memory that never faded, a reminder that in a universe governed by conservation, the past is never fully gone. It keeps moving, it keeps shaping, it keeps deciding what futures remain open, and that may be the most unsettling conclusion of all. The direction the planets moved today was set by accidents so small they would have been impossible to notice at the time. Yet those accidents still matter, still constrain, still echo. All the planets orbit the sun in the same direction, not because that outcome was special, but because once it began, the universe refused to let it be undone. And in that refusal, quietly and without drama, a stable world became possible. At this point, the idea has almost come full circle. What began as a simple observation has turned into a statement about limits, about what the universe allows and what it resists. But there's one last refinement worth making, because it sharpens the meaning of that shared direction even further. We often talk about the solar system as if it were a thing sitting in space, but it's more accurate to say it's a process still unfolding. The orbits you imagine are not tracks carved into emptiness. They are ongoing negotiations between gravity and motion, recalculated every instant. The only reason they look smooth is because the rules underneath them are so consistent. That consistency is what allows memory to persist. Not memory in conscious sense, but physical memory. The kind that doesn't care what you notice, only what you try to change. Direction, once embedded, becomes expensive to alter. It demands energy, it demands disruption. It demands an event big enough to overwrite history. And that requirement is why the solar system still looks the way it does. No such event ever arrived. This makes the shared orbital direction feel less like a curiosity and more like a boundary line. On one side of that line is everything that could happen gently: gradual formation, slow evolution, long-term stability. On the other side are only violent rewrites, close stellar encounters, massive intruders, catastrophic instabilities. Our system stayed on the quiet side, so when we return one final times to the opening simplicity, all the planets orbit the sun in the same direction, the meaning has changed completely. It's no longer a statement about planets at all. It's a statement about time, about how the past constrains the present, about how small beginnings, once locked in, define enormous futures. The solar system is not orderly because order was guaranteed. It is orderly because disorder never gained enough leverage to take over. The original spin survived. The disk survived. The memory survived. And that's the quiet takeaway worth carrying with you. The universe doesn't just create structures, it commits to them. Once motion begins, once direction exists, reality builds around it rather than erasing it. All the planets orbit the sun in the same direction, because the universe keeps its promises, not loudly, not intentionally, but relentlessly. And as those worlds continue their slow paths through space, they carry that ancient promise forward, one orbit at a time, long after the moment that first set them turning has disappeared from view. What's easy to miss once you understand how the solar system inherited its direction, is how ordinary that inheritance actually is. Not ordinary in the sense of boring, but ordinary in the sense of being unavoidable. The universe does not need to decide to rotate. Rotation is what happens when nothing is perfectly arranged. We tend to imagine the early universe as a kind of blank slate, matter evenly spread, motion canceling motion, everything balanced. But that picture only works on paper. In reality, the universe has never been that tidy. Even in its earliest moments, matter was not distributed with perfect symmetry. Tiny fluctuations existed. Regions were slightly denser than their neighbors. Paths crossed imperfectly. Directions failed to cancel by the smallest imaginable margins. Those margins were enough. Once gravity enters the story, even weakly, imbalance stops being a nuisance and becomes a seed. Matter drifts towards slightly denser regions. As it does, sideways motions accumulate. Not because something pushes them into existence, but because nothing eliminates them. Every near miss, every uneven pull, every delayed arrival adds a fraction of motion that cannot be undone later. This is why rotation is so common on cosmic scales. Clouds rotate, stars rotate, galaxies rotate. Even clusters of galaxies show coherent motions. Not because rotation is imposed, but because gravity amplifies whatever motion survives long enough to matter. Imagine trying to stack coins perfectly so that every tiny offset cancels out. One coin shifted by a fraction of a millimeter ruins the symmetry. Now imagine doing that with trillions of particles, all moving, all interacting, all subject to slightly different forces. The miracle would not be rotation. The miracle would be its absence. This reframes the solar system yet again. Its shared orbital direction is not evidence of special treatment. It is evidence of normal physics playing out without interruption. The same process that flattened the protoplanetary disk and aligned the planets is the same process that gave the Milky Way its slow spin, and the same one that causes spiral galaxies across the universe to rotate like vast cosmic pinwheels. But here's the subtle part. While rotation is common, alignment is fragile. Direction is inherited easily, but coherence is hard to preserve. It requires time without catastrophe. It requires a relatively calm environment. It requires that nothing large arrives late enough to rewrite the system's memory. Most systems don't get that luxury. This is why astronomers see warped disks, tilted orbits, and misaligned spins elsewhere. Not because the rules are different, Songi, but because the histories are messier. Direction forms early, but it can be damaged later. When it isn't, the result looks deceptively clean, like our own system. And this cleanliness has consequences far beyond aesthetics. When orbits share a direction, relative velocities stay low. Encounters become glancing rather than catastrophic. Over time, this favors growth over destruction. Small bodies survive long enough to collide gently and merge. Larger bodies clear paths instead of shredding everything around them. In systems where directions are mixed, the opposite happens. High-speed encounters dominate, orbits destabilize, lifetimes shorten, order struggles to persist. So the solar system's shared direction is not just a historical curiosity. It's part of the reason the system lasted long enough to matter at all. And now, the intuition flips one final time. We often think of rotation as something added to a system. But in reality, rotation is what's left when nothing cancels perfectly. Stillness is the special case, not motion. To erase rotation entirely would require conditions so precise they border on impossible. Every particle would need a mirror twin. Every sideways drift would need an equal and opposite partner arriving at exactly the right time. Over astronomical scales, that level of coordination never happens. The universe doesn't aim for neutrality. It tolerates imbalance, and gravity rewards it. Which brings us back to that deceptively simple picture of planets circling the sun in agreement. That picture is not a law being obeyed. It is the visible trace of a deeper truth. Once motion exists, reality organizes around it rather than erasing it. The planets orbit the same way because they were born into a moving system, survived within it, and never encountered an event powerful enough to reverse its memory. Direction didn't need to be chosen, it only needed to be preserved. And preservation, in a universe like this one, turns out to be far easier than erasure. Because once you accept that direction is inherited, preserved, and difficult to erase, you're forced to confront a quieter implication. Not everything that can be imagined is physically reachable. Some futures are closed off, not by barriers, but by bookkeeping. By the fact that the universe remembers what it is already committed to. We used to thinking of physical limits as speed limits or energy limits. The speed of light can escape velocity, fuel constraints, but the deeper limits are historical. They come from what already exists in motion, from what cannot be undone without paying an impossible price. Angular momentum is one of those limits. Once a system like the solar system forms, its total rotational character becomes locked in. You can move pieces around inside it. You can trade motion between bodies. You can redistribute energy. But you cannot erase the overall direction without exporting that motion somewhere else. And exporting it requires interactions so violent, they would dismantle the system entirely. This is why there is no gentle way to reverse all planetary orbits. No gradual process that flips the solar system like a coin. Any attempt to do so would involve catastrophic encounters, close passes with massive stars, or collisions on scales that would obliterate planets long before the direction changed. In other words, the solar system's shared direction is not just how things happen to move. It defines what kinds of changes are even possible. This matters because it reveals a broader pattern. The universe doesn't just constrain motion, it constrains transformation. It allows evolution within boundaries, but it does not allow arbitrary rewrites. History is not editable. It's only extendable. That has consequences all the way down to the human scale. When engineers plan spacecraft trajectories, they don't fight the solar system's motion. They exploit it. Gravity assists work precisely because planets are already moving in coherent directions. A spacecraft borrows momentum from a planet's orbit, stealing a tiny fraction of its motion. The planet doesn't notice. The spacecraft gains enormous speed, but notice what never happens. The spacecraft never reverses the planet. It never meaningfully alters the system's direction. The scale mismatch is too large. The bookkeeping doesn't allow it. This is the same reason hypothetical technologies that involve rearranging planetary systems always sound suspiciously magical. Moving planets, flipping orbits, reshaping stellar systems. These ideas ignore the cost of rewriting angular momentum on massive scales. They treat direction as cosmetic. Physics does not. Direction is structural, and once you see that, a subtle existential implication appears. The universe is not a playground of infinite possibility. It is a landscape of constrained pathways. Some futures are reachable only if they were compatible with the past. Others are excluded, not by rules written in advance, but by motion that already exists. This doesn't make the universe less rich. It makes it more coherent. Because coherence means predictability. It means the same kind leads to the same kinds of futures. It means stability can exist at all. Without these constraints, systems wouldn't persist long enough for complexity to emerge. Everything would be perpetually reset by chaos. So the very thing that limits change is also what makes structure possible. That trade-off shows up everywhere. Stars shine steadily because their internal motions balance collapse and pressure in a long-lived configuration. Galaxies maintain shapes because rotational motion resists total collapse. Planetary systems remain navigable because their shared direction prevents constant catastrophic crossings. Life itself depends on these limits. Long-term climate stability requires orbital stability. Orbital stability requires coherent motion. Coherent motion requires inherited direction that was never erased. In that sense, the direction the planets orbit is not just a fact about astronomy. It's part of the precondition for having a world where anything slow, complex, and fragile can exist at all. But there's a deeper boundary hiding underneath this realization. Because if angular momentum cannot be destroyed, only redistributed, then there are transformations the universe simply cannot perform. It cannot cleanly reset itself. It cannot start over locally without exporting consequences elsewhere. Every action has a cost that must be paid in motion. This is why time reversal remains a fantasy. Why perfectly undoing events is impossible. Why entropy and irreversibility dominate large-scale behavior. Direction in space is tied to direction in time more deeply than our intuition likes to admit. When a system collapses and spins up, it chooses a path forward that cannot be retraced without undoing every interaction that created it. The same collisions that aligned the disk, the same frictions that dampened chaos, the same exchanges that stabilized orbits, all of that would have to be reversed with impossible precision. The universe doesn't prohibit that reversal explicitly. It just makes it unimaginably unlikely. So limits emerge not as walls, but as probabilities so extreme they might as well be laws. This reframes the idea of freedom in a physical universe. Freedom does not mean anything can happen. It means many things can happen, but only along paths compatible with what already exists. The solar system is free to evolve, but not free to forget. And that insight loops us back, quietly, to the opening observation. All the planets orbit the sun in the same direction. That statement now carries a different weight. It is no longer about alignment. It is about irreversibility, about the universe's unwillingness to unwind what it has already spun. The shared direction is a marker of commitment. Once motion began, reality built on top of it rather than resetting it. Once collapse amplified a tiny imbalance, the future became constrained by that choice, not chosen but made real. And here's the calm. unsettling takeaway. The universe does not optimize for possibility. It optimizes for consistency. It does not ask what could be. It asks what must follow from what already is. The planets move the way they do, because changing that would require breaking the system that made them. And the universe, for all its violence elsewhere, never found a reason to do that here. So the solar system remains what it is, a long-lived memory of motion, still unfolding, still constrained, still honoring a direction set by accidents so small they vanished the moment they occurred. Except for one thing, they never stopped moving. There is a quiet discomfort that appears once you truly accept what conservation implies. It's not dramatic. It doesn't feel like a warning. It feels more like realizing a door was never unlocked to begin with. We often imagine the universe as something we could, in principle, rearrange if we were clever enough. Given enough energy, enough technology, enough time, perhaps we could rewrite large systems, move planets, reorder orbits, reset outcomes. But the shared direction of the solar system exposes a harder truth. Some changes are not forbidden. They are just unreachable. Because to change direction is not to nudge an object. It is to rewrite history. Angular momentum doesn't care about intention. It doesn't care about goals. It only tracks what exists and insists that the accounting balance. To reverse a system's overall rotation, you must move that motion somewhere else. You must export it. And exporting it means interacting with something even larger. This is why there is no internal solution. No clever rearrangement of planets can flip the solar system's direction from within. You would need an external partner massive enough to absorb the difference. A passing star, a close stellar flyby, a catastrophic encounter that would shred the system long before it accomplished your goal. In other words, the cost of reversal exceeds the value of preservation. This introduces a sobering boundary, not a boundary of knowledge. We understand the mechanism well enough, but a boundary of agency. There are truths we can know without ever being able to act on them. Structures we can map perfectly, but never meaningfully alter. That boundary appears everywhere once you learn how to see it. You cannot reverse a galaxy's spin without destroying the galaxy. You cannot reset a star's collapse without unmaking the star. You cannot erase a system's past without paying a price larger than the system itself. This is not because the universe is hostile. It's because it is consistent. Consistency creates history. History creates limits. And those limits are what give time its arrow. The reason time feels one-directional is not because the laws forbid reversal. On microscopic scales, they often don't. But on macroscopic scales, the bookkeeping becomes impossible to unwind. Too many interactions, too many exchanges, too much motion distributed too widely. The solar system's direction is one of those distributed records. Every orbit, every resonance, every tiny gravitational exchange has encoded that original spin into countless degrees of freedom. To reverse it, you would need to reverse all of them simultaneously, with perfect coordination. That's not prohibited by logic, it's prohibited by reality. This is why the past feels fixed, not because it is sealed by decree, but because it is entangled with everything that came after it. The more time passes, the more expensive reversal becomes. And this has a quiet implication for how we think about the universe. The universe is not a sandbox. It is not a place where any configuration can be reached from any other if you try hard enough. It is a branching structure, where early paths constrain later ones, and some branches can never reconnect. The solar system chose a branch when it collapsed with a tiny net rotation. Not consciously, not deliberately, but irreversibly. From that moment on, certain futures were possible, and others were not. That is what the shared direction ultimately tells us. Not just how planets move, but how reality commits. How it allows variation but not amnesia. How it evolves forward, but does not cleanly rewind. And this realization carries a peculiar kind of humility. We live in a universe where enormous structures are shaped by microscopic accidents, and then protected by laws that refuse to forget them. We can observe these structures, we can learn their rules, we can even exploit them, but we cannot step outside the ledger. The planets orbit the sun the same way they always have, because the universe remembers how they started, and refuses to pretend otherwise. There's a phrase that sounds comforting when you first hear it. The direction doesn't matter. Clockwise or counterclockwise, left-handed or right-handed. From a purely physical standpoint, the equations don't care. Flip the system, mirror it, reverse the arrows, and the rules still work. That statement is true, and deeply misleading, because while physics does not prefer a direction, reality does not reset once a direction exists. Indifference at the level of laws does not translate into indifference at the level of outcomes. The universe doesn't choose which way to spin, but once spinning begins, the choice stops being abstract. To see why, imagine watching a coin spin on a table. At the moment it's flipped, there's nothing sacred about the direction it rotates. Clockwise would have been just as valid as counterclockwise. But once the coin is spinning, everything that happens next depends on that choice. Friction interacts with it differently. Wobbles develop in specific ways. The exact path to collapse is locked in. The arbitrariness exists only at the instant of origin. After that, consequences take over. The same is true of the solar system. The original cloud could have collapsed with the opposite sense of rotation. Nothing in physics forbade it. But once one direction won, by the tiniest imaginable margin, that victory became permanent, not because it was important, but because it existed. This is a subtle distinction we often miss. We confuse not special with not consequential. The direction of planetary orbits is not special in the sense of being preferred by the universe, but it is consequential in the strongest possible way. It defines a branch of history. And branches do not reconnect. Once the disk formed and flattened, once planets began accreted within that flow, reversing direction was no longer a symmetric option. It would require undoing the entire collapse, reversing every collision, and coordinating every interaction in perfect opposition. The mirror image exists only as a hypothetical. Reality picked one side and moved on. This is why symmetry breaking is such a powerful idea in physics. Many systems begin with symmetric rules and end with asymmetric outcomes. The laws allow multiple possibilities, but the act of becoming selects one. After that, the system behaves as if the choice had always been inevitable. The solar system feels inevitable in hindsight, but inevitability is often just history seen from the wrong end. And this matters because it reveals something uncomfortable about prediction. We like to imagine that if we knew enough, we could foresee everything, that the universe is deterministic in a clean, controllable way. But systems that amplify tiny asymmetries undermine that fantasy. The initial rotation of the solar nebula was so small it could never have been measured in advance. It was buried in thermal noise, turbulence, and random motion. Yet it shaped billions of years of structure. This is not chaos in the popular sense, but it is fragility. Outcomes that depend on details too fine to track, which means that even in a universe governed by strict laws, the specific world you get is contingent. This is where direction stops being a geometric curiosity and becomes a philosophical constraint. The universe is lawful, but not prescriptive. It enforces rules, not outcomes. It allows multiple futures, but only one becomes real. Once that future begins, everything else is lost. The planets orbit the sun in the same direction because one version of the solar system survived and all others never existed. Not because they were impossible, but because they were not chosen by circumstance. This reframes the idea of cosmic luck in a quieter way. It's not that Earth was destined to form. It's that once the system settled into a stable configuration, certain possibilities became protected. Stability created persistence. Persistence allowed complexity. Complexity allowed observers. The direction didn't cause life, but without it, the system might not have lasted long enough for life to appear. And that leads to an unsettling realization. Many of the features we treat as background conditions, orbital alignment, rotational coherence, long-term stability, are not guaranteed. They are historical survivors. They are traits that endured because nothing disrupted them early enough to matter. This means that the universe is not optimized for producing worlds like ours. It merely allows them under narrow circumstances. The solar system is one of those circumstances that worked. Once you accept that, the shared direction of planetary orbits stops feeling like a minor fact and starts feeling like a prerequisite that barely made it through. And here's where intuition fails again. We tend to think that once a system forms, it exists independently of how it formed, that the past dissolves into the present. But in systems governed by conservation, the past never dissolves. It embeds itself. Direction is embedded. Momentum is embedded. Structure is embedded. The solar system is not a snapshot. It is a continuation. And because of that, the idea of starting over, of rewinding cosmic processes, becomes almost meaningless. There is no neutral state to return to. Only earlier states that were already biased, already leaning, already carrying the seeds of what would follow. So when we say the direction doesn't matter, what we really mean is this. The universe didn't care which direction won. But once one did, it cared immensely about keeping the books balanced. Indifference at the start does not imply flexibility later. This is the deep trap hidden inside symmetry. Symmetric laws create asymmetric realities, and asymmetric realities are stubborn. They don't politely offer alternatives. They move forward, accumulating consequence. Which brings us back, once again, to the quiet fact that began this entire journey. All the planets orbit the sun in the same direction. At first, it looked like a rule. Then it looked like an inheritance. Now it looks like a commitment the universe made accidentally, and then refused to revoke. And if that's true here, it's true everywhere. Every rotating galaxy, every spinning star, every aligned system is carrying the same message. Not that the universe prefers order, but that once order begins, undoing it is far harder than creating it. That realization doesn't close the story. It opens a more unsettling question. If so much of reality is shaped by early-gun unmeasurable asymmetries, then how much of what we see today was decided before there was any meaningful sense of choice at all? That question is waiting. There is a moment in every physical process that almost no one notices, because nothing dramatic seems to happen. No explosion, no sudden structure, no visible decision. And yet, once that moment passes, the future is no longer free. The solar system had one of those moments. Long before planets existed, long before the sun ignited, long before there was anything recognizable as a system, the gas cloud that would become all of this crossed an invisible threshold. Not a boundary you could draw in space at, but one defined by dynamics. After that point, certain outcomes became overwhelmingly likely, and others quietly disappeared. This is the uncomfortable truth about systems governed by conservation. They don't wait for structure to form before they commit. They commit early, when everything still looks fluid and undecided. By the time objects appear, the story is already mostly written. The initial rotation of the solar nebula was one of those early commitments. At the time, it meant almost nothing. A faint bias buried in turbulence. A statistical residue of countless interactions that never quite canceled out. No observer could have pointed to it and said, "This will decide the architecture of a planetary system," and yet it did. Once collapse began, that faint bias was no longer optional. Gravity amplified it relentlessly. The cloud flattened, the disk formed, the direction locked in. From that moment on, reversing the outcome would have required undoing the collapse itself, something the universe is remarkably bad at doing. This is what makes early noise so powerful, not because it is strong, but because it arrives before resistance exists. In mature systems, large changes require large interventions, but in embryonic systems, even tiny influences can dominate, because nothing has stabilized yet. There is no inertia of structure, no established pathways, no memory except the one being created. Think of a path through fresh snow, the first person to walk through leaves, faint footprints, barely noticeable, but every person who follows deepens them. Soon the path is obvious. Eventually it's the only practical way through, not because it was optimal, but because it was first. The solar system's direction is that kind of path. Once the disk formed, everything that followed reinforced it. Planetesimals accreted within the flow. Collisions damped misaligned motion. Growing planets cleared orbits that disagreed too strongly. The system didn't debate alternatives. It filtered them out. And here's the part that tends to unsettle people the most. There was no later moment where this could be revisited. No checkpoint where the universe reconsidered its options. By the time planets existed, it was already too late. This is what physicists mean, often quietly, when they talk about irreversibility. Not that laws forbid reversal, but that the cost grows faster than any mechanism could realistically pay. The past becomes embedded in too many degrees of freedom. Every collision, every interaction, every gravitational exchange spreads information about the original direction further into the system. The more time passes, the more places that information hides. To erase it, you would have to find all of it, perfectly, simultaneously. That is not something nature does by accident. So the universe moves forward, carrying its early noise with it, frozen into structure. This reframes how we think about chance. We often imagine chance as something that acts late, a lucky collision, a fortunate orbit, a narrow escape. But the most important chances act early, when the system is still soft, when nothing resists being shaped. By the time we notice outcomes, chance has already done its work. The direction of planetary orbits feels like a detail we could imagine changing. But the window where that change was possible closed billions of years ago, before there were planets to observe. And this pattern repeats everywhere. Stars end up with spins that reflect the turbulence of their birth clouds. Galaxies carry angular momentum inherited from primordial density fluctuations, even on smaller scales. Systems remember early imbalances long after the conditions that created them have vanished. The universe is not forgetful, it is accumulative, which leads to a deeply counterintuitive conclusion. Much of what we perceive as stability is actually fragility that survived. The solar system feels robust now, but its defining features were set when it was most vulnerable. Once that vulnerability passed, the features hardened. This is why the idea of control over cosmic systems is so misleading. We imagine intervening in mature structures, nudging them into new configurations. But the truth is that the leverage points were in the past, before structure, before coherence, before resistance. By the time a system looks stable, it is already committed. The planets orbit the sun the same way today, not because that arrangement is actively enforced, but because the opportunity to choose differently no longer exists. And that realization quietly reshapes how we think about possibility. The universe does not keep its options open indefinitely. It narrows them early, then spends the rest of time exploring the consequences. Freedom is front-loaded. Determinism is what follows. Once you see this, the solar system stops looking like a machine and starts looking like a historical artifact, not static, but constrained. Not designed, but settled. And this raises a question that we haven't yet allowed ourselves to ask directly. If so much of reality is decided before structure exists, if early noise becomes destiny, then where, exactly, does predictability break down? That question doesn't belong to astronomy alone. It belongs to the limits of knowledge itself, and that's where we go next. There's a comforting belief that sits quietly beneath much of modern science. The idea that if we knew enough, if our measurements were precise enough, if our models were detailed enough, then the universe would become fully predictable, not just in principle, but in practice. That uncertainty is merely a temporary inconvenience, waiting to be conquered. The solar system's shared direction gently but firmly contradicts that belief, not because the laws are unknowable. We understand them remarkably well. Gravity behaves consistently. Conservation laws hold without exception. The equations that describe collapse and rotation are not mysterious. And yet, none of that knowledge would have allowed anyone to predict, in advance, the exact direction the planets would orbit. The information simply wasn't available in time. This is a crucial distinction that often gets blurred. A system can be deterministic and still unpredictable. Determinism means that the outcome follows from the initial conditions. Predictability requires that those initial conditions be knowable, measurable, and stable under scrutiny. In the case of the solar system, they were none of those things. The original asymmetry that decided the system's direction was buried in microscopic fluctuations, turbulent motions, thermal noise, tiny gravitational nudges from passing matter. These details were not just difficult to measure, they were physically erased almost as soon as they occurred, folded into collapse and amplified beyond recognition. By the time the sun ignited, the cause was gone, but the consequence remained. This is why hindsight is such a dangerous illusion in physics. Once we observe the outcome, planets orbiting neatly in one direction, it feels obvious that it had to happen this way. But that clarity is retrospective. The universe did not announce its choice beforehand. It revealed it only after alternatives had vanished. And this is not a rare situation. It is the rule for systems that amplify small differences. Whenever a process magnifies early noise into large-scale structure, predictability collapses long before determinism does. The outcome is fixed, but the path to it cannot be reconstructed in detail. The past becomes opaque, even as the present becomes stable. This is why cosmology, despite its mathematical rigor, is filled with probabilistic language. Not because reality is fuzzy, but because access to its earliest moments is limited by physics itself. Information dissipates, signals stretch, interactions scramble details beyond recovery. The solar system's direction is one such lost detail. We know it came from a tiny imbalance. We know that imbalance was inevitable, but we can never know its exact origin. And this imposes a sobering boundary on scientific ambition. We can explain why all planets orbit the sun in the same direction. We can simulate how such systems form. We can even reproduce similar outcomes in models. But we cannot rewind the actual system and watch the decisive moment occur. That moment is gone. This is not a failure of technology. It is a consequence of scale. As systems grow, they bury their origins under layers of interaction. The early universe is not hidden because it is distant. It is hidden because it has been overwritten, not erased, but encoded into forms that cannot be uniquely decoded. Direction is one of those encodings. It tells us that something happened, but not exactly what. And this realization changes the character of knowledge itself. Science is not the art of perfect reconstruction. It is the art of constrained inference. We learn what must have been true, not what exactly occurred. In the case of planetary motion, we know that the initial cloud had net angular momentum. We know that collapse amplified it. We know that no later event erased it, but the precise configuration of particles, forces, and interactions that tip the balance is forever inaccessible. The universe does not archive its drafts. This is why the dream of total predictability fades as systems grow more complex, not because laws break down, but because information does. Early choices echo forward, but the echoes do not carry a full transcript. And this has implications beyond astronomy. It tells us that some aspects of reality are fundamentally historical. They cannot be derived from first principles alone. They require an origin story, one that can never be fully told. The direction of planetary orbits is one such story. It is legible as a consequence, but illegible as a narrative. And yet, this limitation is not a flaw. It is what allows stable structures to exist at all. If every detail remained accessible, no system would ever settle. Everything would remain perpetually sensitive, perpetually unstable. The universe trades reconstructibility for durability. Once the solar system committed to a direction, it gained longevity at the cost of reversibility. It became predictable in the future by becoming opaque about its past. That trade-off appears everywhere. Weather systems lose information about initial conditions within days. Ecosystems encode history without preserving detail. Even biological evolution carries marks of ancient contingencies that cannot be retraced precisely. In each case, early noise becomes destiny, and destiny becomes structure. This is why the idea of full control over natural systems remains a fantasy. Control requires not just knowledge of laws, but access to leverage points. And leverage points exist only when systems are young, soft, and undecided. By the time we arrive as observers, those windows have long closed. So the solar system's shared direction is not just a fact about motion. It is a demonstration of a deeper limit. There are truths we can explain, but never replay. We can understand why the planets orbit the way they do. We can calculate their futures with astonishing accuracy. But the moment that decided their shared direction lies beyond recovery, sealed not by ignorance, but by physics. And that realization invites a calmer, more honest view of the universe. Not as a puzzle we can solve completely, but as a story we can understand well enough to respect its constraints. The planets move together because they always have. They always have because the universe decided early. And it decided early because it could not do otherwise. Where knowledge stops scaling is not where mystery begins. It is where history takes over. And that boundary is not a failure of science. It is one of its most important discoveries. It's tempting to assume that once a planetary system forms, stability is the default. That after the chaos of birth, things naturally settle into long, quiet orbits, ticking away reliably for billions of years. But this assumption comes from living inside one of the rare systems where that actually happened. The universe does not favor stability. It tolerates it. Most systems never make it through their own formation intact. They fragment, they destabilize. They tear themselves apart before anything recognizable has time to emerge. The reason we don't feel this instability is not because it's uncommon, but because systems that fail don't leave much to observe. The shared direction of planetary orbits is one of the signatures of having passed through a very narrow corridor. That corridor exists because gravity is unforgiving. Collapse concentrates mass, but it also concentrates motion. Too little angular momentum, and everything falls inward violently, producing stars without planets, or systems that erase their own disks before planets can grow. Too much angular momentum, and collapse stalls, matter flings outward, and nothing binds tightly enough to persist. Between those extremes lies a thin band where disks form, flatten, and survive long enough for planets to assemble. Within that band, shared direction becomes not just likely, but essential. It's what allows the disk to dissipate energy without destroying itself. Direction is not decoration, it's a stabilizer. When material in a disk moves coherently, collisions are less destructive. Relative velocities stay low. Interactions damp rather than amplify chaos. This gives the system time for grains to stick, for bodies to grow, for orbits to circularize. Remove that coherence, and time disappears. High-speed crossings dominate. Collisions pulverize instead of merge. Growth is replaced by erosion. So the planets orbiting in the same direction is not a side effect of formation. It is part of the mechanism that allows formation to complete. And even then, survival is not guaranteed. Young planetary systems are violent places. Giant planets migrate. Resonances shift. Bodies are ejected. Some systems lose most of their mass. Others are rearranged beyond recognition. What remains at the end is not a pristine outcome, but what managed to avoid catastrophe. Our solar system passed through that gauntlet with remarkable restraint. Not because it was protected, but because its early conditions kept it from escalating its own chaos. The shared direction kept interactions gentle enough to avoid runaway instability. The disk dissipated smoothly. The giant planets settled without triggering total collapse. This calmness is deceptive. It hides how easily things could have gone wrong. A slightly more massive early Jupiter could have destabilized the inner system. A closer stellar flyby could have warped the disk. A different timing of migration could have scattered planets into extreme orbits. None of these events would violate physics. They simply didn't happen here, which means the solar system's stability is not evidence of inevitability. It's evidence of luck constrained by law. And this is where the idea of a narrow corridor becomes useful. Planetary systems are not free to explore all possibilities equally. Most paths lead to short lifetimes. Only a few lead to long-lived order. Shared orbital direction is one of the markers that a system entered that corridor early and never left it. This reframes the role of chance again. Chance did not determine everything. Laws did. But laws alone do not guarantee survival. They merely define the corridor. Chance decides whether a system enters it and whether it stays there. Once inside, direction becomes protective. It reduces destructive encounters. It lowers the probability of violent outcomes. It buys time, and time is the rarest resource in the universe. Long-lived systems are the exception, not the rule. Stars live millions to billions of years, but planetary architectures often change much faster. Many systems rearrange themselves long before conditions settle. Others never settle at all. The solar system endured because its early dynamics avoided amplification of chaos. Its shared direction kept energy flowing smoothly instead of catastrophically. This has a sobering implication for how we think about worlds elsewhere. When we search for planets, we are not just searching for rocks in orbit. We are searching for systems that remained inside that narrow corridor long enough to become interesting, long enough to develop climates, long enough to allow chemistry to explore complexity. Direction alone doesn't guarantee this, but without it, the odds collapse. So the planets orbiting the Sun in the same direction is not a guarantee of habitability. It is a prerequisite for durability. And durability is what makes history possible. This is why the solar system feels almost boring in its regularity. No extreme tilts, no wildly crossing orbits, no obvious scars of late violence. Boring, in this context, means survived. The quietness of the system is the result, not the absence of early danger. Once you see that, the shared direction stops feeling like an aesthetic preference and starts feeling like a survival trait. And that pushes us toward an uncomfortable thought. If stability is rare, if long-lived systems must pass through narrow corridors, Then what does that say about our own presence here? It suggests that we are not standing on typical ground. We are standing on ground that made it through. Which means the calm we experience is not representative of the universe as a whole. It is representative of the small subset of places where chaos failed to win. The solar system is one of those places, and that realization quietly raises the stakes of the story. Because if direction, coherence, and stability are all connected, then the next question is unavoidable. What happens when that stability eventually ends? That question doesn't belong to the distant past. It belongs to the future. There is a comforting assumption hidden inside the idea of stability. The belief that once a system survives its birth, it has earned permanence. That endurance implies immunity. That order, once established, simply continues unless something dramatic intervenes. But the universe doesn't work that way. Stability is not a destination. It is a pace. The solar system did not become stable and then stop changing. It became stable in the sense that its changes slowed down enough to be survivable. The violent phase ended, but motion never did. Energy never did. Exchange never did. Every orbit you imagine is not a closed loop. It is a slow negotiation. Planets trade angular momentum with one another. Tides raise bulges that lag slightly behind rotation. Energy dissipates as heat. Orbits drift by distances too small to notice over a lifetime, but enormous over geological time. The system looks frozen because our clocks are small. This is where another intuition quietly fails. We tend to imagine change as something that arrives suddenly, an impact, an explosion, a disruption. But most cosmic change is incremental. It accumulates silently, carried forward by the same conservation laws that prevent abrupt erasure. Direction is conserved, but distribution is not fixed. Over time, angular momentum migrates. Inner bodies can spiral inward. Outer bodies can drift outward. Spins slow. Orbits circularize. Resonances shift. None of this violates conservation. It fulfills it. This is why stability always contains the seed of its own evolution. A system that conserves motion must continually redistribute it. And redistribution, given enough time, reshapes architecture. The solar system has been doing this for billions of years. The moon is slowly receding from Earth, carrying angular momentum away from Earth's rotation. Earth's day is lengthening, not because anything is wrong, but because conservation demands compensation. Energy lost to tides must go somewhere. Jupiter's interactions subtly sculpt the asteroid belt. Neptune's presence defines the structure of the outer disk. Even the sun is not static. It loses mass through radiation and solar wind, gently loosening its gravitational grip. None of these processes threaten immediate collapse, but they guarantee that the system of today is not the system of tomorrow. This is the quiet paradox at the heart of long-lived order. The same rules that protect it from sudden destruction ensure that it cannot remain exactly as it is. And that leads to a deeper, more unsettling insight. There is no such thing as permanent stability in a universe governed by conservation and time. There is only slow change that respects the books. The solar system feels eternal because its timescales dwarf ours, but on cosmic clocks, it is already mid-transition. The sun is aging. Its luminosity is increasing. Planetary climates are shifting. Orbital resonances will evolve. Nothing dramatic needs to happen for the system to eventually become unrecognizable. This does not diminish its success, it defines it. A stable system is one that changes without tearing itself apart, one that evolves within constraints rather than rebelling against them. One that survives long enough for observers to notice patterns and mistake them for permanence. And this reframes the idea of an ending. The solar system will not end in a single moment. There will be no universal alarm, no instant where direction suddenly fails. Instead, the system will continue honoring its early commitments, while slowly exhausting the configurations compatible with them. The sun will expand, inner orbits will shift. Some worlds will become uninhabitable long before anything dramatic happens dynamically. Direction will persist, even as relevance fades. This is not tragedy, it is consistency. The universe does not tear up contracts. It lets them run their course. And that course is long enough to feel eternal from the inside. Which brings us to a sobering but oddly comforting realization. The shared direction of planetary orbits is not a promise of forever. It is a guarantee of continuity. Nothing more, nothing less. It tells us that change will be slow, that history will be respected, that the future will grow out of the past rather than overwrite it. In a universe that could easily have been far more chaotic, that restraint matters, because the alternative is not excitement, it is erasure. Systems that change too quickly never become legible. They never host memory. They never accumulate story. They flicker and vanish. The solar system did not flicker, it endured. And in doing so, it accepted the cost of eventual transformation. This is the deeper lesson hidden inside that simple observation about direction. The planets orbit the sun the same way not because the universe promised safety, but because it promised continuity. Because it promised that once motion began, it would not be arbitrarily undone. And continuity, given enough time, always leads somewhere else. We are not witnessing a finished system. We are witnessing a system in the long middle, formed, stabilized, slowly changing. Still honoring a direction chosen long before it knew what that direction would one day mean. And as that long unraveling continues, calmly, predictably, without urgency, it invites one final shift in perspective. Not about how systems form, not about how they survive, but about what it means to exist inside one briefly while it does. That is where we go next. It's one thing to understand that the solar system is a survivor. It's another thing to realize what that survival does to you, personally, even if you never think about it. Because you are not watching this from outside the system. You are inside it. Everything you know about up and down, about day and night, about seasons, calendars, navigation, even the idea that the future will resemble the past, rests on the quiet coherence of motions that began long before Earth existed. The fact that the planets orbit the sun in the same direction feels distant and academic until you notice what it implies. You live inside a memory that is still moving, not memory as nostalgia, memory as constraint, as continuity, as a physical record that never got erased. On the human scale, we experience this record as regularity. The sun rises, the year repeats, the sky behaves. We build our schedules on the assumption that celestial mechanics will continue to be predictable. We don't wake up wondering if the planets have decided to reverse. That assumption is so deep, it almost doesn't feel like an assumption at all. It feels like reality itself. but it is a gift of coherence. If the solar system had formed with planets on mixed directions and chaotic inclinations, the sky would not have been a slow, stable clock. It would have been a noisy, uncertain environment. Predictability would still exist in principle, because the laws would still be lawful. But it would not be practical. The sky would not offer itself as a reliable reference. And early humans, without knowing any physics, would have felt the difference, not in the language of angular momentum, but in the language of trust, in the ability to notice cycles, to build calendars, to predict seasons, to plant crops at the right time, to navigate by the stars. Civilization depends on clocks that don't lie. The solar system's shared direction is part of why the sky became a clock instead of a spectacle. This is the kind of connection that is easy to dismiss because it sounds too grand. But it isn't grand. It's mundane. It's what stable really means. It means the environment offers patterns that remain patterns long enough for intelligence to exploit them. Even the modern world, which feels disconnected from the heavens, is built on the same quiet predictability. Satellites remain in orbit because orbits are stable. GPS works because orbital motion is consistent enough to model precisely. Communications rely on geometry that doesn't drift unpredictably. You can't build a global timing system on top of a universe that constantly rewrites its own arrangements. So the coherence of planetary motion is not just a background detail. It is a foundation for a certain kind of life, a life that can make plans. And it's not just practical. It changes the nature of knowledge. Science itself depends on the idea that repeatability exists, that if you observe a pattern today and again tomorrow, you're seeing the same underlying rule, that the universe does not change its laws between measurements, that phenomena can be predicted, not perfectly, but reliably enough to test. This is what the solar system's direction symbolizes in a deeper sense. It symbolizes continuity. It says that the universe has a history, and that the present is linked to the past by rules that don't break their own logic. Without that link, science would not be impossible, but it would be something else. Less like understanding, and more like bookkeeping without access to the ledger. You could still record what happens, but the confidence that rules endure would be weaker. A coherent sky reinforces the idea that reality is coherent, and that feedback loop matters. You might never think about orbital direction while using your phone, but you are benefiting from it anyway. And once you see that, the solar system's shared direction starts to look less like a scientific curiosity and more like a background condition of your existence. Not a reason for your life, but a reason your life could unfold in a world that stays legible. This is why the phrase living inside a memory is not poetic exaggeration. It's literally true. The solar system is carrying a record of its origin forward, and you are living inside that record. You are not separate from the system's constraints. Your day length, your seasons, your climate stability, your night sky, your ability to navigate and predict, all arise from the same dynamics that aligned the planets billions of years ago. And that realization does something subtle to your sense of scale. It shrinks you in one way, because it reminds you that the decisive moments happened without you, before Earth existed, before the sun was fully born. The universe committed early, and you arrived later to live inside its consequences. But it also enlarges you in another way, because it shows that understanding is possible even when agency is not. You cannot change the solar system's direction, but you can understand why it exists. You can see the thread that connects a fainter symmetry in a collapsing cloud to the predictability of tomorrow morning. That is a kind of power the universe does allow, not control, but comprehension. And comprehension comes with a quiet humility, not the humility of defeat, but of honesty. The recognition that the universe is not obligated to be legible to creatures like us. Yet here we are, living in a region where it became legible enough for minds to form and ask questions. The shared direction is not proof that the universe is friendly. It's proof that the universe is consistent, and that consistency, by chance and law together, created an island of calm large enough to host a world. But calm islands have coastlines. When you start thinking this way, you naturally begin to wonder about the boundaries, about the places where coherence breaks, about what the solar system protects us from, and what it cannot. Because beyond the safe, predictable motions that support our lives, the universe is filled with systems that did not pass through the narrow corridor, systems where disks warped, where orbits flipped, where stability never took hold, where time did not get the luxury of patience. Those places exist under the same laws. They just lived through different histories. And that is the next step in the ladder. If we live inside a coherent memory, then the most important question becomes not how that memory formed, but what happened when we try to leave it, when we try to travel, communicate, and extend ourselves beyond the calm corridor that made us possible. That's where the story starts to feel less like astronomy and more like a boundary of civilization. And that's where we go next. There is a moment in every long explanation where the question quietly shifts. At first, we ask why something is the way it is. Then we ask how it formed. But eventually, if we follow the thread honestly, the question becomes more personal and more uncomfortable. What does this allow us to do? The shared direction of the solar system doesn't just explain where we came from, it defines how far we can reach. Because every attempt to move beyond our immediate environment, to send machines outward, to imagine journeys between worlds, to plan futures that stretch beyond Earth, runs into the same constraint we've been circling this entire time. Motion is not free, direction is not negotiable, history is not optional. When we launch a spacecraft, we do not start from rest. We start already moving at tens of kilometers per second around the sun. The Earth is moving. The sun is moving. The galaxy is moving. Every trajectory is built on top of inherited motion. This is not a complication. It is the foundation. The reason interplanetary travel is even possible with limited fuel is precisely because the solar system is coherent. Planets move in predictable paths. Their directions are aligned. Gravity assists work because motion can be borrowed rather than fought. A spacecraft does not overpower the system. It cooperates with it. But notice what this cooperation requires. You must move with the flow. You must accept the direction that already exists. Trying to go against the system is prohibitively expensive. Trying to escape it entirely is harder still. This is the practical face of everything we've discussed. The solar system's shared direction defines a corridor of travel. Inside it, navigation is possible. Outside it, energy costs explode. The universe is not telling us we cannot go far. It is telling us how we must go if we want to survive the attempt. And this scales up quickly. Leaving Earth is hard. Leaving the solar system is vastly harder. Leaving the galaxy is almost unimaginably difficult. Not because there is a wall, but because there is too much motion to undo. Too much inherited momentum that must be cancelled, redirected, or carried with you. Every deeper layer adds another commitment you did not choose. This is where the idea of freedom quietly breaks. We like to imagine the future as open, limited only by technology and imagination. But the universe does not start from a neutral baseline waiting for us to act. It starts from where it already is. We are not explorers stepping onto blank maps. We are travelers navigating currents that were flowing long before we arrived. The shared direction of planetary motion is one of those currents. It doesn't forbid exploration, it channels it. It makes some paths natural and others nearly impossible. It shapes what progress can look like without ever announcing itself as a rule. And this brings us to a calm but sobering realization. The universe is not built for intervention. It is built for continuity. The same conservation laws that preserve the solar system's direction also preserve everything else that matters at large scales. They protect stars from arbitrary disruption. They protect galaxies from sudden rearrangement. They protect history from being rewritten cheaply, which means that intelligence, once it appears, inherits limits. It did not negotiate. We can learn, we can predict, we can plan, we can extend ourselves carefully along the corridors that exist. But we cannot demand that the universe reorganize itself to suit our ambitions. This is not hostility, it is structure. And structure, paradoxically, is what makes intelligence viable in the first place. If the universe allowed easy resets, easy reversals, easy overrides, nothing would last long enough to understand anything. There would be no stable platforms for knowledge, no persistent environments, no long arcs of cause and effect to study. The solar system's shared direction is part of why we live in a universe that can be known. It ensures that yesterday resembles today closely enough for learning to accumulate. It ensures that predictions remain meaningful. It ensures that effort compounds rather than dissolves. So when we talk about limits, limits of travel, limits of control, limits of rewriting, we are not talking about obstacles placed in our way. We are talking about the same constraints that made us possible. The universe did not optimize for expansion. It optimized for consistency. And consistency is what allows slow, fragile things like life and thought to exist at all. This is why the solar system feels almost protective without being designed to be. Its coherence shelters us from constant disruption. Its predictability gives us time. Its direction gives us a frame of reference that doesn't drift beneath our feet. But that protection is passive. It does not extend outward indefinitely. Beyond the calm corridor, the universe remains what it always was: vast, indifferent, and constrained by its own history. Systems form and fail. Motion accumulates. Direction locks in. Survivors persist quietly while countless alternatives vanish without record. Our presence here does not change that pattern. It merely allows us to notice it. And noticing it changes something subtle in how we think about our place in the universe. We are not at the center of a design. We are inside a successful configuration, a configuration that inherited a direction, preserved it, and changed slowly enough to remain legible. The planets orbit the sun the same way, not because that outcome was necessary, but because once it happened, it became expensive to undo, and nothing ever paid that price. That is the final, practical implication. The universe does not protect outcomes. It protects processes. Once a process begins and survives, it continues until something stronger interrupts it. The solar system was never interrupted. And because of that, we are here, briefly, inside a motion that began long before us and will continue long after we are gone. That realization does not demand awe. It invites calm. We are not passengers in a machine. We are participants in a long, conserved movement, one that does not hurry, one that does not reset, one that carries its past forward without asking permission. And once you see that, the question, why do all the planets orbit the sun in the same direction, stops being a question about astronomy. It becomes a statement about what kind of universe this is and what kind of futures it quietly allows. It's worth returning one last time to the simple thing that started all of this. All the planets orbit the sun in the same direction. At the beginning, that felt like a diagram detail. A rule to memorize, something tidy and forgettable. But now it reads very differently. It reads like a boundary condition, a line drawn early in the universe's history that everything else had to respect. That shared direction is not a preference. It's not a design choice. It's a record of motion that survived, a trace of imbalance that was never erased, only amplified, distributed, and carried forward. The planets don't orbit together because the universe wanted order. They orbit together because once motion began, the universe refused to undo it cheaply. Gravity collapsed matter, conservation preserved direction, and time did the rest. What followed had to fit inside what already existed. Seen this way, the solar system is not a finished object. It's a long-running consequence. A structure still honoring a commitment made before there were planets, before there was a sun, before there was anything solid at all. That commitment placed limits on what could happen next. It made some futures reachable and others effectively impossible. It slowed change enough for stability to exist. It allowed patterns to repeat, clocks to work, predictions to matter. It carved out a narrow corridor where complexity could persist. And inside that corridor, a world formed. And on that world, observers appeared. Not to change the direction, not to rewrite the past, but to notice it. The quiet takeaway isn't that the universe is orderly. It's that the universe is consistent. It carries its past forward. It does not reset. It does not forget. It builds futures that must respect what already exists. All the planets orbit the sun in the same direction because reality keeps its books balanced, relentlessly, impersonally, and without exception. And that's not a limitation to be frustrated by. It's the reason anything lasts long enough to be understood at all. The motion continues, the memory holds, and the door closes softly there.